Okay, so we're going to round out this conversation about equilibrium constants by discussing a couple technical terms. And I want to encourage you to pay real close attention here because these technical terms are going to make nice boxes for your head. They're going to really help us understand why things do the things that they do. Okay, so the first term is homogeneous equilibrium. And a homogeneous equilibrium, let me get my marker out. A homogeneous equilibrium is one in which all of the reactants and products are present in the same phase. You guys know what phases are? Liquid, solid, gas, right? Aqueous, okay? Those are the only four phases that we ever think about when we're talking about equilibria. So they have to all be in the same phase in order for it to be a homogeneous equilibrium, okay? Most commonly, reactants or products are either in the aqueous phase or the gas phase. I should use a highlighter every once in a while, shouldn't I? Let's try that for a little bit. Most of the equilibria thus far have been homogeneous, so if you haven't been paying attention to it, it's likely that we have been doing homogeneous, so don't worry about it. But we are going to be watching out for it, and that's what this conversation is about. All aqueous and gas phase species appear in the expression, but not liquids or solids. Do you see that? All aqueous and gas phase species appear in the Kc of the expression. All right, so let's look at a couple examples. So look at this. Aqueous, that shows up. Liquid, that's not aqueous, it doesn't show up. This one shows up and this one shows up. So Kc for this reaction is the products, right, over the reactants. So let's go here. The products are hydronium and fluoride, right? And when this does not show up because it's not an aqueous or gas, but this one does. So this is going to be HF, and this is the equilibrium constant for the reaction which I've shown you above. Hydrofluoric acid plus water gives hydronium ion plus fluoride. So let's do another one. Go back to red here. Kc here is going to again be products over reactants. And you see gas, gas, and gas. And so we are going to say C2H4, H2, and C2H6. My handwriting is a little messy, but I think you get the point, right? So this is an H, not a U. It's that thing right there. And that is the Kc for this reaction. All right, so all aqueous and gas phase products or reactants show up in the Kc expression. All right, so for a gaseous chemical equilibrium only, if you have only gases, then we have another way of expressing Q and K. And we can do that in terms of the partial pressure. Let me go back to red. So partial pressure of a gas is directly proportional to its concentration, and so the ratios have a similar form. Okay, so we would say in this case, if we're doing not Kc or Qc, we might say Qp, where we do the partial pressures now instead of concentrations, right? So remember, partial pressure of C is going to be written like that. Now the partial pressure is also going to be raised to the molar coefficient, right? Still raised to the molar coefficient, just like the concentrations, but now we're dealing with partial pressures. All right. So the reaction quotient for a gaseous reaction can be written as a function of its partial pressures, and the equilibrium constant can be written as the partial pressure equilibrium constant, and we would say Kp. All right. So how are these related? Kp designates an equilibrium constant derived using partial pressures, which I said just a moment ago. Kc designates equilibrium constants derived using concentrations. We use brackets for this one, and we use partial pressure of whatever for that one, right? Now, partial pressures are equal, or rather the partial pressure equilibrium constant is equal to that times this factor. If there's a change in moles, we'll describe this on the next slide. If there's a change in moles, then that's the exponent for R and T. Let's look at these a little more care, okay? So delta G is the change in the number of moles of gas, and R is just the same thing we've used before, right? Except, liter atmospheres per mole Kelvin. That's right, okay? And T is temperature in kelvins, right? So when the number of moles of gas change, then that becomes a significant factor. I think I've got an example here in the next slide. No, I don't. I better give you an example here, okay? So let's say that we've got some gas, NH3 gas. It produces, let's say, nitrogen plus hydrogen, right? So this is not balanced, so let's balance this out. Use red to balance it out. It turns out that's going to be 3, and that's going to be 2, and it's now balanced. Agreed? Okay, so if these are all gases, what is the number of moles of gas in the end? Number of moles of gas final is equal to, that's 3 here and 1 there, that's 4. And the number of moles of gas initial is equal to 2. Do you see that? And so the change in the number of moles of gas is going to be 4 minus 2, right? It's going to be 2, okay? So in that case, Kp is going to equal Kc, whatever I didn't tell you what the Kc was for this reaction, but suppose we knew it, it would be R times T, I didn't tell you the temperature either, squared, right? Can you see that? That's where I get the delta N. All right, we'll do that in practice. Now, some reactions contain reactants and products that are in different phases. All right, these systems are called, and this is an important term, we won't use it a lot, but we do need it, heterogeneous equilibrium. Okay, and that's if the phases are not the same. So you see we've got gases here and a solid here. So pure, and this is a very difficult thing to appreciate in the beginning. We're going to practice it. Pure liquids and pure solids do not appear in the K expression. So K for this then is going to be products over reactants, right? But this is a pure solid. Can you see that? And so this is not going to appear. It's just going to be 1. Okay? And this will be ammonia, and this will be HCl, hydrogen chloride. All right, and that would be the K for this particular reaction because it's a heterogeneous equilibrium. Yes, that's very weird. We'll practice it. Now, the position of equilibria is independent of the amount of solid or liquid present. In other words, this expression doesn't even depend on this at all. Look, at ammonium chloride doesn't even show up in there, right? But it does actually matter that there is some present in the reaction mixture in order for you to verify that indeed you do have equilibrium. All right, so we'll practice that with lots and lots of practice problems. This is just an introduction to homogeneous equilibria and heterogeneous equilibria. Let's go practice.